difficult questions I had a look at in the topic of materials, so I thought we'd have a look at it. It's a question about Young's modulus, stress strain calculations, and I put a few prompts on the board if you wanted to have a go yourself. So just to start with, it's giving you the Young's modulus of steel, it's giving you the cross-sectional area, it's told you how much the strain changes for each rise in temperature, it's given you a value of strain, and it's also given you the temperature. It's asked for the force here. So because it's given you Young's modulus and strain, so strain here, and Young's modulus 2 times 10 to the 11. By the way, I just realized these are very small, so I'm going to rewrite these powers out. This was 10 to the power of minus 3. This was 10 to the power of minus 5. And this here says 10 to the power of minus 4. Sorry, I'm not sure why it's so small. Okay, let's use these now to do the rest of the question. So first of all, we can find the stress because we're given the Young's modulus and strain. I just made a note here, capital E. Normally it stands for energy, but it can also stand for Young's modulus. If we take the Young's modulus of 2 times 10 to the power of 11 and multiply that by the strain that is given, 3 times 10 to the minus 4, that will get you the stress, which in this case is 6 multiplied by 10 to the power of minus 7, positive 7 I meant to say. And then once we have the stress, we can now make that equal to force over area, because we want to find that tensile force over cross-sectional area, which is also given in the question as 7.5 times 10 to the power of minus 3. 7.5 times 10 to the power of minus 3. From here, you can multiply both sides by this cross-sectional area to get the force alone. So the force is the, instead of writing out the whole numbers again, I'm just going to write stress times area. That's the stress of 6 times 10 to the 7 multiplied by this whole cross-sectional area, which in this instance will get you 4.5 multiplied by 10 to the power of 5 newtons. Let's make the power a bit bigger. Sorry, I'm still getting used to writing with this interactive whiteboard, so if my writing is not the best, I apologize. Let's move on to part 2. Calculate the elastic strain energy stored in a rail of unstressed length of 45 meters. That means that, well, without being stretched, its length, capital L, is 45 meters. But then it also says that it's pre-strained, like in part A. That means it has this value of strain, 3 times 10 to the power of minus 4. So we could have just automatically used the fact that energy, so here capital E stands for energy, is a half times the force. Because it says it's like in part A, we can use this force here, multiplied by the extension, but we don't know how much it extends. That's why we have to use the strain equation. We take the value of strain from before, 3 times 10 to the minus 4, and we make it equal to the extension divided by this unstretched length that it mentions. Multiply both sides by 45 and you'll get your extension, which in this case will be 1.35 times 10 to the minus 2. I also just made a little note here that in different specifications, extension can be represented by different variables. So it can be x, like we're using in this question, it can be little e, or it can be like change in length. Great. Once we've got this extension, we can now put it into this equation, and we say that the energy is a half times the force from part A, because it's pre-strained like in part A, so 4.5 times 10 to the 5 that we calculated, multiplied by the extension, which is 1.35 times 10 to the minus 2. You can put all that into your calculator and it will get you a value of 3.04 times 10 to the power of positive 3 joules, because it's a measure of energy. Great. That was 3 marks, by the way. It's just been covered by this here. Let me remove that actually. Yeah. Oh, sorry, it's 2 marks. Don't know why I wrote 3. Okay. Now part C, which most students struggle with in this question, calculate the temperature at which the steel becomes unstressed. So earlier on in the question, it says here that the amount of strain is 2.5 times 10 to the minus 5 for each Kelvin rise in temperature. And it's also giving you a value of strain, 3 times 10 to the minus 4. So if we take the actual value of strain and we divide it by how much strain causes a rise in 1 Kelvin in temperature, which is giving you the value of here. So it says that when there's a strain of 2.5 times 10 to the minus 5, that causes a rise in 1 Kelvin of temperature. And we're dividing that from the actual amount of strain that is being experienced. That'll give you a value of 12 Kelvin because it's being measured in Kelvin. I think that's the hardest part of the question to grasp. If you have any questions about that, just let me know in the comments. But then we use the fact that the rise in Kelvin is equal to the rise in degrees. So if there's a rise in 12 Kelvin due to the strain that's experienced, then we add that onto the actual temperature before it's stressed. So it says that it was laid at a temperature of 8 degrees. But then after that, it undergoes all this stress, it undergoes this strain, which causes it to rise 12 Kelvin, which is essentially rising 12 degrees. So it reaches 20 degrees. Hopefully that made sense. If you have any questions, again, just let me know in the comments. Otherwise, thanks for watching. Please like the video, comment like I mentioned, and subscribe with post notifications on. I'll post a video every single day. And if you have any tutoring inquiries, I've linked my email in the description, so you can just shoot me an email and I can respond. Thanks for watching. Have a good day.